This lesson is on graphing, in particular with using tables. A graph is basically a way of representing all the answers to an equation with two variables. The two variables, for example, could be time and height. In the case of a roller coaster, you could make a graph describing the height of the person as the roller coaster continues on in units of time. This lesson is on graphing. This lesson is on graphing, in particular with using tables. A graph is basically a way of representing all the answers to an equation with two variables. The two variables, for example, could be time and height. In the case of a roller coaster, you could make a graph describing the height of the person as the roller coaster continues on in units of time. Another example of a Another example with two variables is the following. Say you're at a food fair and they have exquisite items such as Zango juice costing $3 per glass and yam wraps costing $6 each. You have $18 to spend. So the two variables are the number of Zango juices you buy and the number of yam wraps you buy. We could make an equation that would look like $3 per Zango juice and $6 per yam wrap to equal $18 total because that's how much you have. So what are some possibilities of buying amounts of Zango juice and yam wraps given the $18 you have to spend? Well, for example, you could say, well, what if I bought 2 Zango juice? Well, that would mean x equals 2, which would then mean you could replace it in the equation. Now, remember, if you bought 2 Zango juice, that would cost you $6, which then would leave you with $12 to spend on your yam wraps, which would allow you to spend the money on 2 yam wraps. So you could have 2 Zango juice and 2 yam wraps. That's one possible combination. So a coordinate point for that would be 2, 2. What else? Well, we can see that 18 can be made by 3 times 6, so what if you had 3 yam wraps? So then you'd have y equals 3. So let's replace the y with 3. That would leave us with no money. So we have no more money to spend on Zango juice, and therefore we can buy 0 Zango juice and 3 wraps. So here's yet another coordinate point that came out of this would be 0, 3. Notice I'm putting my x first and my y second. So those are 2 possible points, but there are many more. Many, many more. So let's take this equation and graph out all the possibilities of purchasing combinations of yam wraps and Zango juices with the money that we have. So let's make a table of values. You've already pretty much filled in 2 points. So from the previous slide we had 2, 2. That was shown in the previous slide on how to calculate that. You basically just replace one variable with one guess and then solve for the other variable. And the other option was 0, 3. So those are our 2 options so far. Next step is to plot the ordered pair solutions on a coordinate system. So let's try that. 2, 2, 0, 3. We have 2 points representing the number of Zango juice and the number of yam wraps. You can see that the pattern could be continued. So for example, the next number here that should work would be 4 Zango juice and 1 yam wrap. Will that work? Well, 3 times 4 gives us 12, plus 6 gives us 18. It sure does. So these 3 points are probably the best representations here. However, you could combine all of those and make a line. Now, every single point on this line should satisfy this equation. Let's continue with some examples. First, we have y equals negative 2x plus 1. So let's practice making a table of values. We want to choose x randomly and replace it in the equation and then find the corresponding y. So let's try that out. Y equals negative 2 times something plus 1. So what do you want that something to be? So let's say we chose x to be 1. Let's replace 1. And that gives us negative 2 plus 1, giving us negative 1. So 1 comma negative 1 is an ordered pair solution. Let's try a few others. We have something at 1, and we want our graph to be sort of spread out. So we probably want to choose 0, and we probably want to choose a negative. We might want to choose a bigger number, but you basically want it as spread out as possible and not all tight in one spot. That way you can see what the whole entire graph is going to look like. So let's choose 3. If we stick in a 3, negative 2 times 3 is negative 6 plus 1 is negative 5. Next, we could choose negative 3. If you choose negative 3, you'll have negative 2 times negative 3 is 6 plus 1 is 7. So negative 3, 7 works also. Let's just try 0 and see what happens. If we stick in a 0, that'll give us 0 plus 1, and that gives us 1. So we've got a bunch of points. Let's plot them and connect them and see what the pattern looks like. 1 comma negative 1, 3 comma negative 5, negative 3 comma 7, and that's off our graph, so that's a little more difficult, and 0 comma 1. So you can almost see this pattern here of points lining up, and you can pull out a ruler and connect the points. All right, what about these ones? What if you had just y equals 1? That's all they give you. Where's the x? There's no x. X is absent. Yikes, what do we do now? Well, that means we can assign him to anything. Meaning, in our table of values, as long as my y value is 1, I don't really care what x is because it has not been forced into being anything. I don't really care what x is because it could really be anything. It's not there to claim its prize. So -3, -2, 0, 1, 2, whatever. So for every x value, your y value is 1. You can imagine that to be filling up this nice horizontal line. What if x is -2? So y is absent. And that also means it can be anything. So in your table of values, as long as your x is -2, I don't really care what y is. Whatever. So as long as your x value is -2, all the possible y's can be used. And that gives you your vertical line. Let's talk a little bit about what makes an equation a line, a linear equation. Well, you've got these two forms you may have noticed with the graphs that we have been making. The ones that had x and y values just plain with no squares, no cubes, no absolute values, they were forming lines. They were linear. The other ones were not. They were curvy. So you usually have a linear equation given in one of the two following forms, either in standard or general form, both terms are used, or a slope-intercept form. We will soon find out why it's called that way in the next upcoming lessons. So you also have x and y intercepts. So this is a key concept because it helps you graph equations in general form when you find the x and y intercept. You may also be asked to find the x and y intercept at any point. So let's talk about how that happens. Say you had a random line, totally random. The x-intercept is the point at which the graph intersects the x-axis, right there. So that's the x-intercept. And the point at which the graph intersects the y-axis is the y-intercept. Now, how would you find these points? These points are basically formed, you'll notice if it's crossing the x-axis, that means your y value has to be 0. So what you can do is you can just plug in y with a 0 and find your x. Same thing goes for the y-intercept. The y-intercept is found when the x values are 0. So you would do the same thing. Similarly, you could plug in x to be 0 and find your y. They're nice and useful when when graphing standard or general form because they give you nice points to start off with.